So for two source interference, which is interference between two waves only, two source interference, that means both waves must come out generally from the same direction like that, then only we can use this formula, lambda equals ax over d. Now what does the lambda represent? The wavelength of the wave that you use. A represents the separation of the sources, which is the from center to center. So if your gap is big, for example, show you or small, this is a small gap, this is a big gap, correct? You still measure the A from center to center, center to center. That's how you measure the A. So in your case, in these both cases, they are both same A, because center to center is the same. Now D represents, the D here represents the distance from the double slit or the two source to the screen. Okay, and the X represents the separation of the bright fringes, or constructive to constructive. But some people ask me, will the separation of the destructive to destructive or dark to dark be the same? So yes, identical. So separation from bright to bright or dark to dark, same X lah. But if it's separation from bright to next dark, then it's half X. Okay, so you can use this whenever it's only for two source interference. Okay, don't use for other cases. Now there's also another thing that you need to know regarding this formula, that whenever the X increases or decreases, it can potentially affect the brightness of the bright fringe. Okay, so what will happen? Example, there are three parameters here that can affect the X. So if I rearrange, okay, I use a next slide. So if you rearrange the equation, you get X equals to lambda D over A, correct now? So there are three things that you can do that will affect the separation of the bright fringes X. Either change the lambda, the D, or the A. Now, if you change the lambda and the D, what happens? Let's do one by one. So let's say talk about D first. If you increase the D, wouldn't the X also increase? Yeah. Now, D represents the distance from the double slit or the two source to the screen, right now. So if you increase the distance, the X will increase. So what will happen to the brightness of the bright fringe? Now some people use the logic that because your D is bigger means moving away, so therefore it will be less bright because the intensity of light will decrease with distance, right? But what about the lambda here? If you increase the lambda, the X also will increase, right? So how will it affect your brightness? Now think about it like this. If let's say my bright fringe and my dark fringe has something like this. Now let's say the X is small. If the X is small, then the bright fringes are also very narrow. So these are my bright fringes. I'm using blue. So between blue and dark means no light. Blue and no light, blue and no light. So the X will be measured from, X will be measured from here to here. Now if the X increases, what will happen is automatically the fringes will get fatter. Then only your X will increase. Because when the X increase means the separation between bright to bright will increase, right now. So it means that the middle, which is a dark fringe, is also wider. Right? The dark fringe must be wider. And the size of the dark fringe is supposed to be equal to the size of the bright fringe. So they're all fatter. So you can imagine that the light which is here now spread over a larger area. So will they get brighter or less bright?
Less bright.
Less bright. So therefore, when you increase the D, you get less bright. You increase the lambda, you also get less bright. But these two together, you can use back the same shortcut if you want, that whenever X increases, the brightness will decrease, X decreases, brightness will increase. But what happens to the dark fringe? Will the dark fringe be affected? That's the next question. Now, the dark fringe is due to destructive interference, right now. So, at destructive interference, what is the resultant displacement or amplitude? 0, right now. So no matter how far you go, no matter what is your lambda, the intensity will be always 0 because the resultant amplitude is 0. So the dark will never get darker or brighter if the two sources have the same amplitude. Unless the two sources have different amplitude, then it will not be perfectly dark. If the two sources have same amplitude, then it will be perfectly dark. But there's Another exception I'll teach you later lah. Okay, now let's talk about A. Now A is very special. You change the A, the X will change as well. Example, if you reduce the A, the X will increase, right now. But the brightness of the bright fringe and the dark fringe will not change at all. That's the exception. Why would it change? Because, give you an example. Let's say I half the A. That means, or maybe I double the A. Okay, let's say I double the A. So if I double the A, wouldn't the X becomes half? So imagine I have this bright fringe. So now let's use red color. So let's say this is my original bright fringe and dark fringe. Okay, so this is my original bright fringe and dark fringe. Now when I double the A, remember the X is half? Separation is half. You can imagine like this fringe separate to 2. That means this fringe separate to 2. This fringe separate to 2. So it's like you cut half. Cut half. So you just give it each one. So therefore the brightness won't change. So therefore for A, right, the X, you change the A, the X will change, but the brightness won't change. Alright, so this is the only exception. So you got to remember this. But let's talk about in real life. So this is ideal. Like in the ideal case, all of them will have equal brightness. And then the dark also equally dark. But in real life, it's a bit of variation. I'll show you in the next slide. Now, we always assume, let's say this is the double slit here, okay, and the middle line is, let's say, here. So we assume that the middle here, the zero order bright fringe, then we assume that the first order on both sides also same brightness, second order and second order also same brightness. So we always assume that all of them have the same brightness. But in actual case, no. The middle one is always the brightest. Then as you go further away, you get less bright. Similarly, next to your middle bright fringe, you're supposed to get perfectly dark, but it's not really perfectly dark. It will be slightly bright. That means not completely dark. You move further away, it is even lighter. You move further away, it was even lighter. So the graph of the, let's say you're measuring the amplitude, right? In the middle is the biggest, right? So here is supposed to be 0, right? But you will actually get a small amplitude, very tiny. Then this one slightly bigger. Then this one slightly smaller. It's like that. So why is it like this? We're talking about amplitude. Okay, why is it like this? Now in the middle, both light can travel equal distances. Okay. So the distance traveled is the same, so we assume that when they reach there, they get the maximum brightness. But if you go further away to the left, the light from this side will travel further, right now. So the amplitude that comes from here is smaller. So when you add to this amplitude, your resultant is smaller. So the further away you go, the further as you travel. So the resultant amplitude is smaller. That's why the bright fringes, as you go away, it gets less bright. But what about the dark fringe? Now, in the middle here, actually not the middle, on the side beside the middle fringe, this one travels shorter than this one. So that means the amplitude from here will be smaller than here. So can they perfectly cancel? No, you cannot. Understand? But if you go further away, then the difference in distance it gets even bigger. This half difference is even bigger. So then the difference in amplitude is even bigger. That's why you get a bigger resultant wave. Understand? So this is in real life how it will look like. Okay. Actually, I should draw this now. Why I draw like that? Weird, huh? Can I redraw this? Okay, anyway, try this while I redraw this. Maybe I should take this photo. What page is it? 5. So if you want to see a better diagram, right, to represent the intensity, it will be something like this. Okay, so you'll notice that center has the highest amplitude, but you notice that this is not completely 0 because it cannot perfectly cancel. Then the resultant amplitude smaller, then this one also cannot perfectly cancel, but this will be higher than this. Alright, then this is even smaller. Then it's symmetrical on the other side.